Hello, guys. Welcome back to MedZone African Motives. We are still on our industrial electronics N3. So in this case, we are going to work with the semiconductor physics to understand what is it that we are required to know in order for us to attempt typical questions such as what we are given in this part. All right. So actually, we are going to start understanding of the composition of matter. So I just hope by the end, you'll be having the knowledge that is required to answer any typical question that you are going to be given, as long it has to do with the semiconductor physics. All right. So like I said, we're going to consider this. All right. So if we are to check, we have got the composition of matter. So that is the first part that you are going to need to understand how the matter is considered. So by definition, we are simply saying the matter is anything that has mass. All right, so anything that you're going to have and it has got mass and occupies space. So that is what you are referring to as the matter. All right, sorry guys, I want to just use this one. So that is mass and occupies space. So as long it occupies space, that is, and such that it is classified into liquid, solid, or gaseous form. Irrespective of the form these materials take, they all consist of what? Of atoms. So the matter, as we are talking about, it also has or consists of an atom. So what is it that we are referring to as an atom? So an atom, it consists of a nucleus, which is situated at its center. So at the center of an atom, that is where we have got the nucleus in that case. So from the nucleus, we are simply referring to a condition whereby we are talking of the protons and the neutrons. Okay, so we are going to talk about that. So that is what we are given. And electrons, so we've got the nucleus and also the electrons which orbit the nucleus. That means after that, whatever that we are having there, these are electrons. The nucleus consists of protons and neutrons. This is what I was talking about, that this because it is the number of protons that you have, that is also the number of electrons. And if you're talking about the neutrons, these are neutral, all right? They are electrically neutral. So since an atom is electrically neutral, the number of negative charges, which is the electrons, equals the number of positive charges of protons, with the neutrons carrying no charge, that is being neutral. There is no charge there. So it is neutral. We're talking about the condition of an atom in general. This is what you need as the properties. So I want you to go through this part, understand everything that you are given, the theory part that you are given. So then now also the major important part, we're going to talk of the positive ion. It has more protons than electrons. That is, it has lost an electron. Whereas a negative ion has more electrons than protons, that it has gained electrons. So this is the structure that we're gonna have, and we were having them, that we gonna have the nucleus, talking of the protons and the neutrons, okay? Then the electrons orbiting the shells that you're given. Then the electron orbits or electron shells. All electrons move around the nucleus in a circular orbit or shell. The shells have been designated, that is K to Q, with the K shell being the innermost shell. So in the innermost part here, we're going to have K. So you're going to have K shell, L, M, N, O, P to Q. These are electrons that you're talking about. So as we can see from the concept of our shells from K up to Q, the inner part, it has got the low energy electrons. As you are moving to the outer part, which are the which is the part of the valence shell. In the valence, you're talking about this one, the outer, the one which is at the outer shell. That's the valence. So the electrons which are on the outer shell are called valence electrons. These are valence electrons. So there we are given that the number of electrons allowed in each shell as we are moving, like from the inner shell going out like that. Each shell, it has got a maximum number of electrons that it must carry. The inner shell, which is the K shell, is supposed to have 2 electrons. Moving on to the other one is supposed to have 8 electrons. So how are we going to know the number of electrons that we are supposed to obtain in each shell? This is where we are given the formula that is to determine the maximum number of electrons in a certain shell. We are going to use the formula 2n squared, where n is the shell number. So meaning to say the K shell, which is the first one, like we said, we are going to use K up to Q. K, L, M, N, and so on. So K is going to be 1, 2, 3, 4, and so on. So meaning to say this is the N, like the shell. This is your N. So that is the number that you're substituting in place of N. If N is 1, which is the innermost shell, it's going to be 2 times 1 squared, which is 2. If you're talking about the second one, 2 times 2 squared, that is 4 times 2, which is 8, and so on. 2 times 3 squared, and so on. 3 squared, which is 9, 9 times 2, which is 18, and so on. So these are the electrons, number of electrons that we have in each maximum. So meaning to say, if you are given, like for an example, you are given a silicon, which has got 14 electrons from the atomic number of 14. It means as you are to represent that silicon, you're supposed to represent it. We have said we have got the 14 according to our atomic number. So meaning to say, as you are to consider your silicon, the first part that you're going to have, which is the innermost shell, which has got 1. So you saw that is we have to use our formula 2n squared, and we have to substitute 1 in place of n, we ended up with a 2. So meaning to say we are going to represent the first 2. We move on to the second shell. In place of n, we substitute 2. So that is 8. So we have already used or covered these 2. So if we use this 8, are we still in within the 14? 8 plus these 2 is 10. So we are still in within the 14. We still have a remainder. So we are going to have 8 in this. That is the maximum that we can have is 8. So we have got 2, 8. Now these are 10. Out of 14, we are remaining with what? With 4. But we are supposed to have like 2, 3 to the exponent of 2, which was going to be 18. But we can't represent these 18 because we are remaining with 4. Out of the 14, we covered 10. So these 10 from 14, we are remaining with 4. So as we can see, guys, the remaining part, which is 4, is in within the 18. So we can just represent our 4, 1 here, 1 here, 1 here, 1 here. Do not just represent like all the 4 at one point. No, they are shared along distributed. So that is the idea there. So given any part that you are given from your elements, you are going to need atomic number. Okay, so this is the part which we are going to talk about in this. All right, so these are also the properties that we have got on an atom that we can have as a summary. So I want you to go through those properties, but this is what I'm trying to say from our elements, the natural elements that you have from this part. We can have we can know atomic number of each element and also the symbols that you're going to have. The atomic number 1, having hydrogen. This is the symbol for hydrogen. So these are electrons per shell. Remember the first one, the second one, the third one, fourth one, the fifth, and so on. So we just have one atom, so meaning, one electron, so means that is going to be 1. So that is what you're given. Atomic number 2, that is helium, the symbol for helium, and so on. The electron per shell, we just have only 2. The lithium, and so on. So I want us to go through all these and understand. So the numbers which are at the end here, these numbers, if you're considering these numbers here at the end, these ones, these are the numbers of electrons in the valence shell, which means we're talking about valence electrons. So if you're talking about these ones that are in within this column, their valence is this part. Okay, from these ones, if you're talking about these ones, this is going to be their valence electrons up to this 8, these ones. So these are the electrons that we have in the valence. If we talk about these elements that we are given here, it means it is going to be 1 up to these ones. These are the ones that you're going to have as your valence electrons. The same part, if you are to consider this part here, it's going to be up to this, just before that one. Okay, if you are considering these 2, that is their valence. Like what that is what we just have. It is the inner shell, it is the outer shell at the end. So this is what you're going to have throughout, guys, up to these ones in this other side. So make sure you go through, understand each and every part that you are given. Like just to do not know everything, guys. Like you're not supposed to know everything on this part. All right, just to understand the basics. So what you need here mostly is to understand these ones that we're gonna mostly work with, especially the hydrogen, the boron, the oxygen. All right, these are some of the most important. The phosphorus. There's something that I'm looking for here. There's something that I'm looking for. The germanium here. All right, where's the silicon? Did I mark the silicon? Did I mark the silicon? All right, I marked the germanium. All right, guys, you see these ones now. They might be not close to me as you might. Okay, this one here, it's because of the phosphorus there. This one, silicon is another part also. So these are the major, and also this potassium, even these argon, sulfur, but just okay. Just know one or two from them. You do not need much from that part. This is supposed to be taken from our elements, okay? Remember, from your elements, you are supposed to have these properties. So this one is just like a summary of all the elements that we are given. So yeah, just know the basics there, revise through your theory. Then we also need to understand about the forces acting on an orbiting electron. So that is, we got the force of attraction. So the force of attraction, I talk about the electrons being negatively charged are attracted to the positively charged nucleus. And we've got the centrifugal force. The electron revolves around the nucleus at high velocities. And as a result, it is forced away from the nucleus. For the electron to stay in its orbit, this force has got equal but opposite to the force of attraction, opposite to the force of attraction that you had before. Then I also need you to go through the energy levels, which is the energy gaps and energy bands, which is also important in your syllabus. They also need you to understand these from the different types, the insulators, semiconductors, and the conductors in terms of the conduction band, the energy band. So they are going to need you to draw these diagrams. So as we can see from our insulators, we have got a condition where this part of the valence band is small, okay, compared to all other bands that we are having. So all this part, they need you to understand each and every part, like how it is the differences that you're going to have between the three. So please just go through your theory, guys, and just go through your theory. So the energy gaps which exist between shells are sometimes called the forbidden energy gaps, since no electrons exist in these regions. Valence electrons exist in the highest energy level shell. For an electron to move to a higher energy level, two conditions must be met. One, there is a vacancy at the higher level. The number two, the electron must acquire enough energy to overcome the energy gap. So the conduction band, it exists at higher energy level than the valence band. For electrons to move from the valence band to the conduction band, they need to acquire some energy. So each movement along the bands, it needs an energy. So that is where we are given the energy gap. So that is the energy is the one that we are referring to. So for insulators, as we can see, the energy gap is big, conduction band very small. Okay, move on to the semiconductors. The valence band is big and the conduction band, but the energy gap very small. Then for conductors, the energy gap, it overlaps. The energy gap, it is overlapping. It overlaps. Take note. On all these ones, we're having a normal energy gap, but when it is for conductors, it's gonna overlap. So when they are asking you, they just need you to draw these diagrams, guys. Are you not gonna be able to draw these diagrams? Okay, so let's just stop you can even memorize if it is like that, that you can't be able to draw your diagrams, then memorize them. Also, they need you to understand the part of the atomic bonds. Just talk of a condition when water is formed. It's a bond that is happening, okay? Formation of water, there is hydrogen, 2 hydrogen atoms and oxygen. Forming what? Water. A molecule of water, H2O, 2 hydrogen and oxygen atom. That is the part of the bond. So just like an example of this water molecule, it can be, we can talk of the ionic bonds, we can talk of metallic bonds. There are different types. Covalent bonds. So all you just need is to know what type of what the bonding that is happening between the two. So we are not going, guys, deep into our chemistry. No. Don't think about that. Don't go through that. So I just want you to go through these bonds and tell the difference between each, so it can help us in our revisions, and also go through your covalent bonds so that you do understand the differences between. So let me just explain about the covalent bonds. This one is it's a condition where we are going to have the valence electron from each hydrogen atom forms an electron pair with one of from the oxygen atom, and each pair is shared by their respective valence shells. The valence shell of all 3 atoms now appears to be filled as in this figure. So this is on a condition that was happening between the hydrogen and what? The oxygen. So when you are given this bonding, when it is happening in semiconductors, the covalent bonding, that is the part that I want to explain this one. You are having the same material. Let's consider what we had before, silicon. We said for a silicon, the atomic number is 14, remember, for a silicon. Our atomic number is 14. So I want you to understand that if you checked there on that part, or the diagram that when I represented, the electrons which were on the outer shell, which are the valence electrons, there were 4. Remember, we covered the first 2, and we covered the 8, and we're remaining with the 4 at the end. So this is what I want you to understand about this silicon, because that is where the bond is taking place. So it's like this. You are having a normal atom, which is your silicon. You're having 14. You have covered, okay, let me just go back, guys, to what we did. We covered the first 2, then another 8. I mean, the other part, which is 8. We are remaining with the 4 electrons at the end. We are remaining with the 4 electrons. These are the ones that I want us to talk about in this covalent bonding of our semiconductors. So considering that we have got so I don't want you to go back to this construction because it is an electron sharing that is happening of the outer of the valence. So meaning we are going to consider what is on the outer shell, those four. So take an example that you have got your silicon. We saw that in the outer, we have got 4 electrons like this. This is what we have in the outer. So if you are to take another silicon to pair to this electron, to pair to this electron, to pair to this electron, another one to pair to this electron, they are having their own 4. So you're going to have a silicon here, okay, with its 4. With its 4. So it's just going to be something like this. I'm just talking about what is on the outer. So it will be having its 4. 1, 2, 3, 4. So as you can see, there is a sharing that is happening there. Another one, again, if you're to present, gonna have somewhere there, another silicon, the same material. 1, 2, 3, 4. That's a sharing. So this is going to happen to each and every part. 1, 2, 3, 4. Another one at this part. Again. So you're going to have 1, 2. That is another 1, 2, 3, 4. It's another silicon. So this pairing, guys, it is going to happen and happen and happen and happen and happen and happen and happen. So there is an electron pair that is happening. So this is the one that is the major part of our covalent bond. If you check what is happening here, if you are to, this is not going to end. We're going to have these guys. From this one, there's another one. There's another. It's going to be, guys, and so on and so on and so on and so on. So these are referred to as the covalent bonds that electron share. That is the covalent bonds. Guys, I hope you understand what is happening. So it is, this type of bonding is of particular interest to us because it exists in all semiconductor materials. So you can bond anything in a semiconductor material. So this is, guys, what we had before. So if you are to check here, we've got the semiconductor crystal structure from that silicon that we had. Semiconductors like germanium, silicon, and silicon are joined by covalent bonds. So remember our germanium in terms of the atomic number is 32, but the valence, it has got 4 valence electrons, which is the same as the silicon. It has got 4 valence electrons. So that is where they have got properties, because the electrons at the end, at the outermost shell, are the same. They've got same number. So these materials, particularly silicon, are the ones used to produce semiconductor devices like diodes, transistors, the silicon controlled rectifiers. and the integrated circuits. Silicon and germanium atoms have got 4 valence electrons, which is the one that I was indicating there in their valence shells. These atoms are referred as the tetravalent atoms. That is the tetra. Guys, remember from tetra, 4. Tetravalent atoms. So please, guys, do revise as much as you can. So in that part, we are also going to talk about this doping, which is one of the most important for us to understand, which is the addition, which is the deliberate addition of controlled amounts of foreign atoms or impurities. So that is an approximate of 1 part in 10% to a pure intrinsic or intrinsic semiconductor. So that addition is the one that we are called as the doping. So this process of doping modifies the electrical properties of semiconductor to such a degree that the conduction is improved. And the new type of conduction is referred to as the extrinsic conduction. Remember, we talked of the intrinsic properties if you were going through this reading properly. Conduction in intrinsic semiconductors is via electron hole pairs and is referred to as the intrinsic conduction. So please go through, guys, that we do understand the pure material, which is the one that we refer as the intrinsic material. These are pure. Then the extrinsic, these are the ones that have been added. There's additional or foreign materials. So they are no longer pure. They are extrinsic. So please just go through and see what you are given. Then, so the condition of the doping process results in either an excess of electrons or holes. If the impurity that was added was a pentavalent, penta from 5, the one that has got 5 valence electrons, there is going to be an excess of electrons whenever you use a pentavalent. So examples of pentavalent atoms, that is where we talk of the phosphorus, the arsenic, the antimony. These are the ones that have got 5 valence electrons. So there will be excess of electrons at the end. However, if a trivalent atom, which is tri, that is 3, the one that has got 3 valence electrons in the outermost shell was added, there is an excess of the holes. The holes, we are talking of the being positive, the electrons negative will result. So a hole is like there was supposed to be a negative, but the negative is no longer there. So it's referred to as a hole. Examples of trivalent atoms are indium, gallium, boron, the aluminium, titanium. These are the ones that you have, the ones that have got 3 valence electrons. So you can even check from that table of summary that we had, any part that has got 3 valence electrons, those are the ones that you are referring to as the trivalent. All right. So as we are to consider the N-type material, meaning to say we have got more negative. And we said for us to have more negative, we must be having what? a pentavalent atom. Anything that has got what? 5 valence electrons, like using phosphorus. So having a bond with a phosphorus, in this case, which has got 5 valence electrons, you are bonding a phosphorus and a silicon. A phosphorus, it has got 5 valence electrons, remember. In the outermost shell, there are 5. In the outermost shell, they are 5. But remember that a silicon, it has 4. So meaning to say we are going to have a silicon here, we are going to have a silicon here, we are going to have a silicon here, we are going to have a silicon here. All right. That's our silicon. Our silicon. But a silicon, it has got 4 valence electrons. That means we've got 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, and so on. This is for a silicon. So by bonding these, you're going to see that, okay, these two, they are taken. 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 There is a negative, this negative. Guys, remember, these are valence electrons. This electron here, where is it going to pay? There is nothing. So this is the free electron. This is the free electron. The covalent bonds happened, but there is a free electron. That is more electrons. That is the N type. So at the end, we are saying it's more negative, the N-type material. So what you just need is to know when is this happening? What is it that you're going to have for you? What do you need in order for you to have that N-type? That is it, guys. The more negative charge are the ones that we have. So just go through, guys, okay? So we need the pentavalent. So we're going to need silicon and anything that is within the pentavalent. You can use any as long it has got 5 valence electrons. Then the p-type, it means at the end, we are supposed to be in short of electrons. We are supposed to be in short of electrons. In short of electrons. That is to have a hole. So using boron, the one that is what is in the under trivalent, which has got 3 valence electrons, we are going to see that a boron has got 3 valence electrons. But being bonded with a silicon, which has got 4 valence, it means we were supposed to have a silicon here. We're supposed to have a silicon. Okay, let me just put this so that because of time, another silicon like this. But remember, a silicon, it has 4 valence electrons. So as you are to bond with a boron, which has got 3 valence electrons, it means we are going to take the 2 here. We are going to take these 2. We are going to take these 2. What about this silicon remaining? Because we do not have an electron to use here. We do not have an electron to use there. So that is the part which we refer to as the hole. We are in short of electrons. So it is an electron hole pair, where an electron is pairing with a hole. Electron hole pair. That is the idea. So this on the boron being the hole, we are in short of electrons. So that's a hole. This is the indication that we are having on this part. So for you to have a P material, it is because you are using what? You are working with a trivalent. Addition of a trivalent atom results in a P type. The one that has got what? 3 valence electrons, e.g. a boron. So guys, just go through your notes. Just go through. Then also the part of the Fermi levels, it is similar to that part that we had on those energy levels. So I want you also to go through this part up to the current in the semiconductors, go through everything, make sure that you do understand all the basics that you are given, the diffusion current, the whole current. These are some of the current, guys, that you can even read and understand by yourself what is it that they are talking about. So anything that is written in red there, it is something that is important for you to take note, to understand. Then also another important part is the PN junction. It's a junction that you're talking about. So from the positive, negative. So considering the PN junction, let's say if an amount of donor impurity atoms are introduced into one side of a single crystal of semiconductor, and equal amount of acceptor impurity atoms into the other side, a PN junction is formed. So remember P being positive, N for the negative. There is the negative on one side, a positive taken to the other side. Remember the force of attraction that we have in our between the electron and protons. Different charges. So as the movement is happening, the electrons moving to the positive, a region is going to be formed. There is going to be a region formed in between, which is referred as the depletion region. That region consisting of something of this nature. Let's say we have taken the negative, has moved here. They are now at this point. Remember, they want to attract with what? With the positive. So it's like this. So we are having positive, positive, negative. Remember the movement of the electrons. It means if you are to connect a battery, it must be like this. The negative, the movement of electrons, the electrons current from positive. So meaning to say we're going to have the movement of what? The movement of current also. So this is what I want you to have. It's actually the PN junction. It's actually a diode. This is the diode application. So this is the PN junction that's formed is also referred to as a diode. At the instant the junction is formed, remember, there is no external supply. The electrons in the region of the junction will cross the junction and combine with the holes close to the junction. So I think, guys, if you go through your notes, you can understand much more because your textbook does not remove some other things as we try to remove other things as we explain. But if you go through your textbook, I think you can understand much better. And the question papers that we are going to have that will add more to our understanding, and also the biasing of the PN junction in terms of the biasing. Now when the voltage is now involved, all is the movement of electrons, reverse biasing. So the normal, which is the forward biasing, which is this one, the positive must be connected to the P. This negative must be connected to the N type. So this is what you call a forward biasing, okay? Opposites the, that is, in this case, we are given the polarity of external source is such that it opposes the barrier potential. The effect of the forward bias voltage is that the positive side of the external voltage repels the holes in the P-type material and causes them to drift across the junction. So that is the most important part when dealing with the forward bias. Then for a reverse, we are going to have the connection now opposite, the negative to the positive connected to the negative. That is a reverse bias. So it can be a forward or it can be a reverse, which is actually best described on the types of diodes that we are going to have later on. If you are talking of a diode, remember a diode, it allows the movement of current in a one way, a normal diode, but we're going to talk about that later on. So that is the semiconductor diode. The semiconductor diode is a two-terminal PN junction device. We are still talking of the same PN junction, but it has low impedance when forward biased and high impedance when reverse biased. This means that the diode acts as a conductor when forward biased, allows current in one movement when forward biased, and as an insulator when reverse biased. So if you reverse bias a diode, there is no movement of current. That is to act as an insulator. It does not allow current to move, to pass through. Does not allow current to pass through. So that's a diode. So you're going to need the symbol and also the characteristics of a diode, depending with the type of a diode that you are given. Is it a silicon? Is it a germanium? Those are the most two in your syllabus. So this is the symbol of a normal diode having the anode and the cathode. Okay, so that is it, guys. So then for the voltages, if you are working, because it's going to be different with, are you working with a silicon or a germanium? So these are the approximate voltages, 0.7, 0.6 to 0.7 for a silicon. For a germanium, 0.2 to 0.3, this is the approximate voltage that you're going to have. So this is the forward bias region that you're working with at a forward voltage drop. We are given a certain forward voltage, and the reverse bias region where we have got the reverse breakdown voltage at this point. So these are the voltages and the current that you're given. And also this is referred as the peak inverse voltage. These are the properties that you need. They are going to need you to draw these characteristics of a diode and the symbol of a diode. Okay, so know your symbol and also the voltage current characteristics of a diode. These guys, just to have this, we want you to know this. So just go through everything that you are given from what we had. It can help you, especially to understand your theory to the maximum. Like to understand, like this part is all about your theory. They are going to ask questions drawing of those I mean the diagrams of when you are having those energy gaps. We remember when we are having the difference between the energy levels, energy gaps, and energy bands. The diode, the symbol of a diode, the characteristic curve. Those are the things that they will be asking you. The doping. Do you know your doping? N-type, like those, like 2 mark, 1 mark questions. So it's like a combination. So I want you to go through, like, understand what is it that you're gonna have. Do more question papers, combine questions under semiconductor physics, combine questions and see how do they ask these questions. So as we saw from that one that we had this, we already talked about this from the notes that we had. So these are the typical questions that will be: show with aid of neat labeled sketches the width of the forbidden gaps of each of the following insulator, semiconductor, and a conductor. I showed you this. Draw the construction of a PN junction diode when it is forward biased. Guys, everything have it. So go through your notes. I want us to go through our notes. Do as many question papers as you can. Where you do not understand, we can talk about that. So in terms of other topics where there are calculations, we're gonna talk about that. But for these theories, where you need to go through everything, just find time to revise back. All right, go through everything just to understand your basics. You'll see that you won't have any challenge, and answer question papers, because if you revise with a certain textbook and you are not revising question papers also, you are bound not to know what are they going to ask from what you are revising. Some information is not that necessary. There is the most important part that they keep on asking. That is the most important part that they need you to understand. Yes, know all the basics, but do not go to exam without understanding, like, how to draw this each separate. Like this, they want you to draw all of this. So the difference between the gaps there is the one that you just need to indicate between the valence band, conduction band, and so on. So we just hope we are going to have more questions done from our question papers that can help. But for now, that's it. Till we meet again.